As I mentioned, today's speaker is Alex Bouchard-Côté. I first heard of his work on the Poisson-Indel process through Leo Pachter, who said that it's the most interesting and exciting development in phylogenetics he saw this year. Alex's PhD advisor was the very well-known Berkeley statistician Michael Jordan. Alex skipped doing a postdoc and went straight to a faculty position in the highly regarded statistics department at the UBC. I'm very happy to have him speaking today, and his talk is entitled The Poisson-Indel Process.
Thank you very much. So it's great to be here with you all today, remotely, I guess. So this talk will be about part of it will be about the Poisson-Indel process, and I'll also talk about another work that is kind of the complement of it, a sequential Monte Carlo method, which allows us to do computation in the Poisson-Indel process. So let's begin. So today the main topic is a string value continuous time stochastic process, this Poisson-Indel process that I'll describe. And the second item on the agenda will be an algorithm to compute posterior probabilities over trees and alignments in this stochastic process. So the goals, the higher level goals for doing this work was to extend the set of phylogenetically informative characters beyond point mutations. So we'll talk about Indel, and also we'll talk about how to move forwards to bigger events as well than just point Indels. And at the same time, we want to still have fast algorithms and algorithms that can be parallelized. So I will start with, I guess, 3 examples of these non-local, non-IID events that we would like to use as phylogenetically informative events. The first one is what's called a slip strand mispairing, so I'll abbreviate that by SSM. And this is a very frequent phenomenon in some data sets, in particular, for example, in chloroplast data sets. And the way it works is I show a short example here. It's from Levinson 87. It is an error during transcription. So here, for example, you see a 2 base slippage and an 80 repeat during a replication of a DNA duplex. And this is followed by a continued chain elongation. And the end result is a long insertion. And if you would have had slippage in the other direction, you would have the long deletion instead. And in non-coding part of the genome, these can be really frequent. So we would like to use them as informative events. But as you can see, these are highly non-local. So you need to know what's besides the long insertion in order to understand that you have to insert or delete or repeat here. And so here so this has been recognized, for example, in the very nice paper by Morrison, 2009, as having large and non-local effects on alignments that are not currently handled by most alignment programs. And on top of that, you still have these point mutations. So this superposition of these two things make the inference of these phenomena non-trivial. So on the left, I show kind of a small tree and a sequence of 2 of these SSMs and 1 point mutation. And on the right, you see that you have a large effect on the correct alignment with only this small number of changes. The second example I want to give is structural constraints. So these are also have been recognized as having large and non-local effects on phylogenetic trees. So I think we have Chris in the audience right now. So he had a really nice paper in 2011 quantifying these effects. Now we would like to go further and actually use these effects as informative events. And also what has been recognized is that just having rate variation is not needed for these type of things. So rate variation will get you part of the way, but you not only want to recognize that there's less or more change in these regions, you also want to recognize that these changes occur at the same time. So this is obviously not that easy. A third example outside of biology, so I'm also interested in linguistics phylogenies, where in some sense we have the ultimate non-local phenomena. So basically the first order phenomena in sound in linguistic change is this thing called sound change, where you can think about it as instead of having a sequence of nucleotides, you have sequence of sounds, and at some point in the tree you have a change where every nucleotide or every sound of a certain type goes to another nucleotide, and this is applied to all sites simultaneously. So we would like, so somehow I'm not going to expand on this, but there's a connection between model for this type of phenomenon and the model, the two first example that I gave before the slide. All right, so this is all very ambitious, and what I'm going to talk about is a foundation for approaching these questions. So the first part will be the Poisson-Indel process, which, as I said, we believe is a useful foundation to build model with non-IID and non-local assumptions. So we have already some tests in example 3, which unfortunately I won't talk about because it's would require too much extra terminology. But we also we're all currently working on example 1 and 2. We don't have results yet, but we think these will be approachable with extension of what I'm going to talk about today. So for this first part, this is joint work with Mike Jordan, as was mentioned in the beginning. And the second part of the talk, if I have time, I will also talk about more details on the actual algorithm used to invert these models using this thing called Sequential Monte Carlo. All right, so as I said, the Poisson-Indel process is a string-valued, continuous time stochastic process. So in particular, it gives you a model for a joint distribution over trees in alignment. So there are joint models over trees in alignment which are not induced by a continuous time process, but we're interested by these continuous time process because they can recognize these events, these ancestral events as phylogenetically informative. We're not necessarily interested in the alignment itself, but it's a hidden variable or partially hidden variable that will be needed to do these and for these trees. There are already obviously many existing stochastic processes that are string valued. So the canonical example is TKF91 and the follow-up TKF92. There are much more sophisticated version published, for example, in Miklos et al. In 2003 and subsequent papers. Now, the advantage we think that the PIP has, why it's justified to have this new process, is that it gives a general mechanism for modeling non-IID and non-local effects. And also computing the probability of a tree and an alignment is cheap, easy to implement, and easy to parallelize. So that's what I'm going to demonstrate in the following slides. So in order to understand this, why computation are easier in the PIP, in the Poisson-Indel process, I'm going to review a little bit how TKF91 works. So here the problem that I'm interested in is I'm giving you a single multiple sequence alignment, a single phylogenetic tree, and we want to compute the probability, if you want, of the multiple sequence alignment given the tree. And if we want to resample the multiple sequence alignment, for example, in the MCMC chain or even SMC chain, we'll need to compute these exactly and quickly over and over again because they will be in acceptance ratios. So just as a notation, I'm going to write P, T, M for this in the following slides. And the question that I want you to keep in mind is why P, T, M is hard to compute in TKF91 and why it's easy or easier to compute with PIP. So just as a reminder, I'm going to describe how TKF91 works. The way I'm going to explain it is not necessarily the way you would usually think about it. Usually it's described as the solution of a differential equation. This way is equivalent, and it has the advantage that it gives a really sharp view on the connection between TKF91 and the PIP process, and also the difference, important difference. So suppose that we start at time 0, and we have the sequence ATC shown here on the top. So this is for one edge in a tree. And we want to find out what is going to be the next event. It could be an insertion, a substitution, and a deletion. And we want to know when it's going to occur. What's the waiting time or the holding time? And in order to do that, a nice algorithm or point of view is to simulate one exponential random variable for each of these operations and each of the location where these operations can be applied. And these exponentials will have different rates. So you read off these rates from a rate matrix. And the smallest of these independent random variables determines the nature of the next mutation and also the time at which it occurs. So here, for example, the winner is yellow, so an insertion before the nucleotide A at the beginning of the sequence. So I apply this operation, and now I start this game again, basically with this new sequence. This is how TKF91 works for a single edge. If you have a tree, what you do is you basically compose this mechanism on each edge of the tree. So one way to view it or describe it is a graphical model on the left, or as a sequence of or a set of string-valued conditional distribution on the right. Now, the difficulty with TKF91 is that if I give you a large tree, the exact computation of this P of tree and alignment is exponential in the number of observed taxa in the worst case. And this is perhaps, yes.
So I didn't want to interrupt, but I just wanted to ask, could you describe a little bit about the process when you actually have a deletion or an insertion? I mean, how big is it drawn from some distribution of lengths, or how does that work?
Yeah, so for the basic TKF91, there will be basically the inventory with probability 1 at each instant in time. There will be at most one substitution or exactly one inserted nucleotide and one inserted or deleted nucleotide. So in the TKF92, there's some mechanism added to add in one chunk a group of nucleotides of length more than one. This creates some artificial auxiliary variable in order to do that. I'm not going to go in these details, but basically with TKF91, you have only point mutation that are allowed. Is that basically yeah, good? Okay. So this is the basic process, TKF91 process. And this is easy to compute if you have only one edge to sum over these paths or a small number of leaves. Now the problem arises if you have a big tree, 10 taxa, 100 taxa, or something like that. And in this case, computing the probability of a tree in alignment, marginalizing over these ancestral sequence and the sequence of insertion deletion that give rise to the observed alignment, this is already intractable. And if you want to do that in the MCMC chain and compute it for many alignment in a row, this is going to be challenging. So there's some clever work. I'll talk maybe at the end about how to make this fast in some situations, but in the worst case, even the cleverest algorithm by Miklos and colleague is still exponential in the worst case. And we don't want approximation because it's an MH ratio, metropolis hasting ratio. So here's the new stochastic process. And what's nice with it is that it's very simple to describe how we're going to modify it. Instead of having, so we're going to keep the structure of the deletion and substitution the same, but instead of having one insertion clock between each nucleotide, we're going to have one global insertion random variable with a constant rate. And if this is the nucleotide that wins, we're going to pick one location at random for the insertion. So this seems like a small change, but the added benefit of this, an important benefit, is that with this change, the location of the insertion, which is a random set on the edge of the tree, is a Poisson process with a deterministic intensity measure on the tree. So just to repeat that a little bit with more explanation, this pi here is a random set, and each of the xi here are the location where there was some insertion. We don't know exactly where in the sequence it was, but there was some insertion, and they give rise to one or more or zero observed sequence in the alignment. And the name of this process is the Poisson-Indel process. Now, going a bit further on what's the consequence of this Poisson process, of this Poisson representation, is that the other mutation, that is the deletion and the substitutions, are exchangeable continuous time Markov chains. So let's basically look at, so we had 3 insertions in that tree that was Poisson distributed. Let's pick one of them, so it's exchangeable, so it doesn't really matter what order we're going to visit them. And conditioning on this insertion at that location, what happens below is can be viewed as a continuous time Markov chain with the state space being equal to the nucleotide that we add. So in general, you would have, let's say, 4 colors for the 4 nucleotides plus an absorbing delete state. So this kind of representation or algorithm has been used in the literature before, for example, in Reddelings et al. In 2005 and Rivas et al. In 2007. The difference is now we get this algorithm emerge as the marginal of a stochastic process. So this is a nice property to have for different consistency reasons. Now, let's see. So once we simulate, so going back to the slide, just the last step, I simulate this process down the tree, and I can look at basically what I get at the leaf, and that gives me a column in my multiple sequence alignment. Now I do that for another points, and I get another columns. And finally, the alignment is just the concatenation of all these columns. Now, the next step, I want to show more precisely, so this was the forward process. I want to show that it's possible to get tractable computation for the inference problem. Now, namely, I observe an alignment and I want to sum over all these internal insertion location, the number of insertion, and all these deletion, substitution that occur across the tree. And I'm going to do that in 3 steps. The first step, so for computing P of T comma M, is to use exchangeability and reduce the computation of this probability for the whole tree and the whole alignment to the computation of the same thing, but with a single column in the alignment. So here the green M is a single column, red M is the full alignment. So I'm going to show you that I can basically, without loss of generality, think about the computation as just a single column. And this follows by exchangeability. And just giving you a short description of the detail, now the only issue that arises is that, so we observe a certain number of columns. So we see that there are 7 columns or 6 columns here, for example. This means that the number of insertion is unknown because some of them could have no observation, but we know that it's greater or equal to 6. But the key thing is that all the observations that do not have any trace in the data are all exchangeable. So we basically have an infinite product that we only need to spend time for each part of the product that corresponds to a column in the alignment. And all of the other one, we only do it once for this term here, computing it once, basically for one empty alignment. And there's this function which we show a closed form that basically gives us what's the total probability for all the unobserved insertion in the tree. So this is kind of the high level of the first step. Now the second step, now we have reduced it to a single column in the alignment. We need to still do the computation for this column. The first step is to identify the branch where the insertion occurred, and this we already know that it must be ancestral to all the non-deleted extant nucleotides S that we see in the column. So S is these 2 nucleotides that I see in the data. And I know the insertion must be on one of these two edges here, just because of the nature of homology. And now what I'm going to do, I need to compute the relative probability of these two events, and I use a Poisson property of Poisson processes that basically, if I condition on the event being on one of these two, the probability that the insertion occur on a branch of length b is proportional to b. And even if you assume an infinite branch on the top, you can still do this computation, it turns out, without going into the detail. So again, this type of idea has been explored in the literature. So there's the Nichols et al. Paper in 2006 and the Alexei and co. paper in 2008. Although these papers were not concerned with an Indel model. So what we did, we pushed that to a full Indel model. Now the final step is basically now that I fix which edge at the insertion, summing over these substitution and deletion is easy using standard matrix exponentiation. So you just think about it as a standard site in Mr. Bayes that you just get the likelihood using sum product and matrix exponentiation. All right, so this is basically the proof or the evidence that this is tractable to do this computation for the PIP model. Now, I just want to give you a rough idea why this computation gets trickier with the TKF91 model. And in order to do that, I'm going to use a graphical model of basically all the quantities that are involved here. So one of them is the tree. One of them is H, the set of homology path. So think about it as basically a column alignment plus all the events in the ancestral nodes. C is a restricted view on an homology path. It's basically just the leaves. And P is a partial order on the column. So basically think about it as, so this first part of the process is done without consideration of the ordering, but at the end there's some ordering on this sequence. So I call that random variable P. And at the end, if you have the set of column and the partial order on them, you can just determine the observed sequence. So we only observe this thing here. And the key difference between PIP and TKF91 is that this partial order depends only on the set of columns in PIP. So it's just basically a permutation 1 over n factorial of these columns. Whether in the TKF91, you need to know the location of the insertion and deletion for determining what is the distribution of these partial order. So basically, since we want to sum over this, having this extra dependency makes things really hard to summarize. So this is the basic idea. Now, this is the work we've done so far. Let me talk about a little bit how it connects to our longer term goals of adding non-ID and non-local effects. The general approach is to first identify a polynomial size inventory of possible non-local effects. So for example, in the structural example, you would, let's say, assume a known structure let's assume it did not change too much in the tree at end. And we're going to assume that the non-local effects are only on a neighborhood of these interaction, let's say. And we're not going to force them all to use these interaction. There will just be some library of possible interaction. For the SSM example, we're going to assume, for example, that the SSM have a bounded length. So that gives us a polynomial inventory. Now, once we have identified this inventory, we're going to represent the full process as what's called a superposition of two Poisson processes. So on the left is basically what we add already. So these are the point Indels, which we can marginalize analytically. Now, we're going to add to this another Poisson process, which are the non-IID effects. And these are very complicated, so we're going to sample them. But since we're able to always marginalize that, it turns out it's possible to construct an irreducible chain where you can move these points around or propose these points around and kind of compute the MH ratio of these different hypotheses using this computation here superposed with this one here. And a nice property is that when you add to Poisson process, that's what's called a superposition, you still get a Poisson process. So you get nice theoretical properties. So this is reminiscent of a 99 paper by Ozenbeck et al., which consider superposition in the case of a pure mutation process. Now the difference is that now we think we have the tool to move that forward to first more than just a substitution process, indels, and including long indels. And also, I'm going to talk in the next of the rest of the talk about a way to actually do inference on these models, not just simulate from these models and evaluate the impact on existing methods, as was done in this previous work. So I'm going to show some very preliminary experiments on this PIP process. This is basically take this as a sanity check that at least for small taxa, it works reasonably well. It improved both the tree and the alignment. And as a nice upshot, we're going to get some quantitative measure on how much improvement tree can be gained from alignment and how much improvement alignment can be gained from resampling the tree. And basically, so this is on small taxa, 7 taxa. This is just because this part used MCMC. Now we're working on applying the second part of the talk to this material, and it's going to scale to much larger trees in the short future. So for now, let's still look at basically what was our baseline here was using tree inference done by PML by Guindon et al. 2004, and sequence alignment by Clustal. So these are some basic baselines that everybody knows about. And so I'm going to evaluate on Robinson folds distance for the trees and adding alignment edge F1 for the multiple sequence alignment. So as a summary, we get, compared to these baseline, we get an improvement of 27% on synthetic data for trees and 43% on synthetic data for multiple sequence alignment on these two metrics. To break down these improvements a little bit, so if we start with the baseline, these two baseline existing system, and we just do resampling of the alignment, we get a 35% improvement on the alignment benchmark. And we get a further 3% relative improvement if we add on top of that, tree resampling. And if we do the process on the other side and evaluate it with tree metrics instead, we get a relative improvement of 16% and then 13%. So it seems that the joint inference process benefits most for improving trees from these preliminary experiments. Okay, so this is what I wanted to say for this first part of the talk. Now let's talk a little bit about how we can, so all this first part was with a fixed tree in a first and fixed alignment, which is not realistic, obviously. So now we want to only start from nucleotide data and
Sorry, could I, before you leave that first part of the talk, could I ask a quick question?
Yeah, please.
So we saw the Poisson-Indel process. I'm not sure if I understood the slide maybe 2, 3 back that you had the black stars and the red stars. So my understanding is the left-hand side with the black stars represents the PIP.
Yeah.
And then the right side represents these non-IID effects, such as like the base pairing and so on. I'm not sure if I really understood how you're modeling these other non-IID effects.
Yes, so I didn't give that much detail because this is still ongoing work. So basically the current way we're dealing with it. So the most concrete one example I can talk about is this example from linguistics where every nucleotide is changed to another one, let's say, okay? And so basically in this, so maybe this phenomenon doesn't occur in biological data set, but you could imagine that, for example, there's a point of the tree where a lot of C goes to G for some reason. Maybe a big change of the optimal growth temperature. I don't know if it's realistic or not, but so basically each of these points you can think about as a pairing of a location in the tree and the specification, so remember I said there's an inventory of change, so you can sample a multinomial from that. So for example, here I sample a multinomial that would maybe be okay, I think that at this point of the tree, this group of observed nucleotide, their ancestor was identical to this other group, and they were obtained through a SSM. So it's a detailed account of what the non-local change should be. And now this point process here, the way it's going to tie in with the PIP is, if I go back to a previous slide, it's not going to change the first part of the computation. It's only going to modify basically this part, where now we look at the effect of we look at the effect on each of the nucleotide, and this is going to modify the graphical model, where instead of having edge here, which are all from an exponential, this edge here, let's say where I know there's a non-local change, I'm going to add a special potential that encodes, say that the nucleotide has to have this certain value at the beginning, and it has to have this other value at the end. So you can think about it as proposing an observed value at an internal point of the tree, which corresponds to this non-local change. I have a slide at the end after talking about the computation, which I think will help clarifying this. So right now, it's very hard to see how you can propose all these non-local change and do the inference. So this is where having the sequential algorithm for inference is going to help. For now, is that reasonable? Okay. Thank you. Let's see. So let's talk about this sequential Monte Carlo inference method. So this is joint work with Srivan Sankara-Raman and Michael Jordan. So there's a paper in Press in Systematic Biology about this. And now the topic of this part of the talk is integration of the space of tree and alignment using SMC. And the motivation is a Bayesian approach to phylogenetic inference. And as a prelude, I'm going to talk a little bit about the simpler problem of maximization over a space of trees, just because it's easier to understand the idea there. Then I'll move on to integration over trees. So just a bit of background, if you want to maximize over trees, there are two main heuristic search strategies that you can apply to max over the space, either local strategy or sequential search. The key difference between these two strategies is the type of tree representation they use. So local strategies use a fully specified state, which is simply a tree over the observed species. And so we worked with state that encode both topologies and branch length. But now let's suppose that it just encodes topology for simplicity. And here's how the local strategy meta-algorithm work. You start at an arbitrary state, and algorithms in the local category first find a set of states that are close to the current one and evaluate them. So you start an arbitrary state, and you evaluate a set of neighbor and you move to a nearby tree. So maybe this one in bold here. And then you repeat this process from this new current state. So an example in maximization for this is stochastic annealing. And the second strategy, sequential search, is based on a different representation, partially specified state or partial states. So in this talk, the partial state would be forest over the observed species. And partial state can also be conceptualized as set of states that satisfy some constraints. For example, having a subtree over species C and D, shown here. Okay, so this is what a partial state is. And this is the connection with all the trees having this constraint here of having this subtree. Now, a sequential strategy works as follows. So you start with an initial unconstrained partial state, so the fully disconnected forest, for example, here. And you look at possible ways of adding a single constraint to the partial state. For example, adding the constraint that this has to be a subtree in the forest. And then we pick a promising extension, and basically each of these extension narrows down the set of associated states. So at the end of the day, if you do that long enough, you'll get a fully specified state, and you get this as your answer. So an example of that is neighbor joining and maximization. So kind of if we look at classification of phylogenetic algorithms, for maximization, we have, I mentioned, stochastic annealing, say for a local strategy, and we have neighbor joining for sequential strategy. And clearly MCMC is a local strategy, and it's an integration algorithm, so we have something here. And SMC comes in to fill this spot here. It's an algorithm for integration using a sequential strategy, where we use partial states in particular. So just to set up a little bit of notation, for this part of the talk, I'm going to assume rooted ultrametric trees. I'm going to use T for trees, X for the hidden sequence, so I'm going to denote the target distribution by pi. It's the tree given the observation. And let's say that it has this density, gamma t over z, where gamma t is basically the joint density evaluated at t comma the observation. And we sum over the hidden x as its standard. So let's think about it for now in an IID model. We'll see how the PIP comes in later. And this Z here is the data likelihood, so it's intractable as well. And we want to compute different expectation with respect to this posterior distribution here. For example, clade support and so on. So just as a background before I go to SMC, let me describe importance sampling, which is the precursor, if you want, of sequential Monte Carlo. And it's you can think about it as starting from the fully unconstrained partial state, sample trees using a proposal Q, and then for each of these, so Q could be arbitrary, for example, the prior. Now for each of these tree, we compute some real valued weights, which is a ratio of the unnormalized density divided by the density of the normalized proposal. And we call these W, or weights, and each of these pairs of partial state and weight is called a particle. And so the problem with this approach is that if pi is i-dimensional, if you have several branch lengths, you're going to have that most particles have tiny weights, and you spend a lot of time computing them, and they don't contribute to the expectation. So basically, another view of importance sampling is that it tries to get to this approximate distribution in one step using a single proposal, for example, the prior. SMC use a sequence of proposals. So we're going to take small step, where at each step we're going to add only one constraint in the partial state, and only at the end we get to the target distribution. And so there's going to be a step called resampling that makes this much more powerful than this. But let's see how it works. With the similar picture, we initialize with the fully unconstrained partial state. And in the first step, we just do an importance sampling step, but for a single constraint. And we sample, let's see. So, do I show the way? Yeah, so so imagine recursively that in the previous step you get a distribution which is basically represented by a population of particles, each of which have a weight. So we can sample from this distribution, and this is this step that we get here. And the effect of doing that is basically the particle with small weights will get an expectation through the weight. So you won't spend time in the future expanding an hypothesis that is probably getting you to nowhere. And you get more copies of the promising states. And now what you do from this new population that you resample, you propose successors again, and you compute weights for each of these. Now the way they are computed is similar to what we've seen for importance sampling, except that now we have a ratio of these unnormalized density. So it looks a little bit like Metropolis-Hastings ratio, except that interestingly, we only have the proposal on the denominator. And you continue this process until at the end you get full trees, and this population of particles gives you an approximation of the posterior over the trees at the end. And an interesting property of this is that it's consistent, meaning that as this number of particles goes to infinity, you approach the true posterior. So as your computational budget increases, you have the freedom of getting exactly the right amount of precision that you would like to have in theory. So just to give you an intuition why this works, let's think about one path in this sequence of proposed partial state, and let's look at all their weights. So recall that all their weights look like a ratio of unnormalized density. And if we forget for now about the resampling step, the final weight of this particle here will be a product of all of these weights here. And this means that these ratio here will telescope, meaning that this one will cancel this one will cancel this one, and so on. And what you get at the end is basically as the same form as the importance sampling algorithm. Another explanation here is that these Q you would use basically just Bayes rule or the chain rule to understand that this is equivalent to the full proposal. But this resampling step gives you a way of not spending time in unpromising particles. This is the key difference with importance sampling. So this is what I was saying. So if you compare the product of these weights, you get the same form as the importance sampling updates, which is a classical result to be known to be consistent. And so I'm going to, because I want to spend more time on the part on non-IID model, I will just quickly tell you about some of the experiments on IID data. So check our systematic biology paper for more information. So in this example here, we give SMC and MCMC a fixed computational budget, which is 10,000 iteration. It turns out that it's a fair comparison because in both cases, the bottleneck is the Felsenstein recursion. And so one particle will cost the same thing as one MCMC iteration. And now we look at synthetic tree of increasing size. And as you can see in this fixed budget regime, SMC does a better job of giving a consensus tree of that is closer to the true generating tree. And yes, and if you have infinite budget, both converge to the same tree because both are consistent, but we're always interested in finite computational time. Especially when we'll add alignment, which will complicate everything. We want these things to be quick for IID model to be able to go to non-IID model. So just another experiment on a comparative RNA data set. So here, we don't have the true tree. So instead, what we do, we compute a consensus log likelihood. We can compute a consensus tree and look at the log likelihood. So it's not an ideal evaluation of Bayesian methods because we care about the distribution, not just the consensus. But it's a reasonable surrogate that you should be able to have consensus of high likelihood. And again, so here higher curves are better. And for finite computational time, we can see that we get higher consensus likelihood. And as I said before, if this time, this axis is time, and if you wait long enough, you get the same result, but we care about these finite times. Okay, so as a summary, I've talked about PIP first, a string-valued continuous time stochastic process. It gives a general mechanism for modeling non-ID, non-local effects. And computing the probability of a tree and alignment is cheap, easy to implement, and easy to parallelize. And I talked about SMC, which is fast and easy to parallelize and allows joint inference of non-local, non-ID events. So basically, these last point here are current work. So I want to talk a little bit more about our current work on extending SMC to the, so actually we're working on several fronts. One of them is to handle non-clock trees. So this was all work, this was all based on clock tree. So we're working on extending to non-clock tree and extending this to joint parameter estimation and sampling of non-IID model. So this current work I'm going to talk about is joint work with Yang Wang and Arnaud Doucet. And so let's start with just the idea of sampling alignment jointly with these trees. Now what we're going to have is, again, these partial state, but they are also going to contain alignment. And initially this alignment is going to be the empty alignment. And as I propose these merger operation, I'm not only going to propose this phylogenetic operation on the tree, but also homology statement on the multiple sequence alignment. Now, if I give you a pair of this, remember that all I had to compute was these ratio of density. And using the PIP machinery, we can compute these really fast. So basically, we can give weights to these particles really fast. And in order to propose them, you have a lot of freedom. You can use existing models or canonical proposal and so on. So this was if you have only alignment. Now let's say that we want to also sample these non-local events. What we would do is basically at each step, we look at this new edge that we propose. And now we only have to propose non-local events and this in a single edge at a time. And this can be done by sampling from this Poisson distribution. And this annotation on the partial state can also, its weight can also be computed efficiently. So just a few words on an interesting issue that comes when you look at these extended post-set SMC algorithm. You get what informally can be thought as an overcounting problem, where some combinatorial structure can be built in a single way. For example, this tree, this unbalanced tree can be constructed in a single way. And this binary tree here can be constructed in two ways, by first merging these two or first merging these two. So in non-clock tree, you have to deal with these. And then also when you have these non-local effects, you have to also handle these multiple ways of building an hypothesis. And we have developed a framework for handling these, which is based on, instead of having only a forward proposal on these structure, we also have what we call a backward proposal, which comes in and corrects these ratios that I've shown earlier in the SMC algorithm. So superficially that looks like an MCMC algorithm, but it turns out you have more freedom on what this Q minus can be. For example, non-reversibility is allowed and interesting things like that. And this gives you basically the freedom you need to propose these non-local change jointly with the tree and alignment. So thank you very much.